All right, so I'll make a start. So yeah, welcome to the second lecture in this course. So I noticed looking at the recording last time, there are actually some audio problems. So if at any point while I'm talking, the audio breaks up, or if you can't understand something, then please just interrupt me and ask me to repeat it. Hopefully we won't have so many audio problems today. So yeah, so I'm going to continue where I left off last time. So in the previous lecture, we saw two vertex models, both of them that live in the general framework of fermionic vertex models. And the simplest one is this one here, so the 5-vertex model. And we looked at its connection with well, non-intersecting lattice paths, and in turn used those to construct the short polynomials combinatorially in a construction that is completely classical and, you know, in all the textbooks that you'll read in algebraic combinatorics on short polynomials. So the 5-vertex model, we associate 4 states to a vertex, so A, B, C, and D. And A, B, C, and D, they take values in the set 0, 1. 2 possible states for every single edge. And as we saw last time, there are some constraints that you place on these vertices. So first of all, the sum of the 2 states that live along here, that has to be equal to the sum of the 2 states that live here and here. And this is just conservation through the vertex. And there was also this property here that prevented 2 paths from kissing in the vertex. So that's the first model we looked at. And then there was a second model, which was slightly more advanced, but the way we formulated it was actually very closely related to the original vertex model. So this one is indexed now by vectors. So maybe we should put a little bar under each of these to indicate that they're vectors. So A, B, C, D, and now these are binary strings. So A, B, C, D take values in 0, 1 to the n. So they're binary strings of length n. Okay. So this model has a lot of features in common with the first one, actually. So again, it has a conservation property. So all of the models have this. The second thing is, again, it has this property here that prevents, you have n species of particles now, and this property here prevents within one species kissing at the vertex. So you can have different species that kiss, but as long as they're the same species, you're not allowed to have kissing, which is this. And then finally, there was an extra indicator function here that basically eliminated the possibility for 2 paths of different colors to cross. And so that was the reason why we referred to this as a sort of compressed colored version of non-intersecting lattice paths. And we saw that the first one of these, this was used to define short polynomials, and this one was used in the representation of the Q-weighted polynomials. Okay. So that's where we got to last time. And notably, in both of these models, there is just a Q parameter. Okay, well, in this one, there is even no Q parameter. But in the examples that we looked at, there was just a Q. And at this stage, we do not have this second notion of temperature that we're interested in, which was this T. So today's lecture is really going to be about bringing T into the picture. Okay. So please feel free to interrupt with questions at any point. I'll try to monitor the chat if there are any questions there. Okay. All right, so now that we've started with something simple, let me show you something that will probably be very scary. So this I refer to as master vertex model. It is by no means the most general type of vertex model that you can get in the quantum group formalism, but it is somehow the sort of the highest level version of the vertex model for which things are still somehow tractable and for which you can get a nice formula for the weights, and it degenerates to all of the special cases we're interested in. So it's for that reason that I call it a master vertex model. Okay, so what's the setup here? So again, your vertex is just going to be one of these little squares. And again, it's just going to have A, B, C, and D around the edges of the vertex. And so this is the precise form of the weights that we put on it. Okay, so I have 4 binary strings, A, B, C, and D. And from this, I define another binary string, which is this V vector. And if you look at V, so basically, so these are either going to be zeros or ones, and most of the time these are going to be zeros. So if you take the min of these 4 things, most of the time you'll get a 0 because one of those will be 0. But in some cases this will be equal to 1, and that's precisely when all 4 of these are equal to 1. So this V is really monitoring the species that kiss. So that's precisely looking for the case where you have this sort of thing happening here. So if color I does this, then that means that V sub I would be equal to 1. And if you don't have that, then all of the other V's will be equal to 0. Okay. So here are the weights. All right, so I'm not going to say too much about these weights. All right, so they depend on 2 parameters. So as I advertised in a previous lecture, we really have 2 parameters that we can introduce to our weights, X and Z. And in terms of symmetric functions, both of these can be used as alphabets for the symmetric functions that show up. So they depend on X and Z. They also depend on this, as promised, this parameter T. Okay, so this T, just to remind you, this is like the quantum group parameter now. This is the quantum deformation. And so this is the explicit form. Okay. So they do look very horrendous, but I want to say a few things about them. So the first thing is that actually, if you go ahead and simplify this thing, so it's perhaps not written in the most simple form, actually you find that these are polynomials in X, Z, and T. So that's not obvious, but basically this denominator will cancel off somehow. So they're polynomials in X, Z, and T, and furthermore, they're polynomials with positive integer coefficients. So this is nice. So in a sense, it's a sort of combinatorial model. The other thing about it is it's fully factorized. So by fully factorized, I mean that you know explicitly the roots if you view this either as a polynomial in X or Z. And most importantly, there is behind this a Yang-Baxter equation. So there is some intertwiner which actually intertwines these tiles. And there is an explicit formula for the weights of the intertwiner as well. So you have a very explicit Yang-Baxter equation, which we're not going to write down, but nevertheless, this is the model. And so this model, as far as I know, it was first introduced in the recent work that we had with Amol Agarwal, Alexei Borodin, and that's already from January this year. So as far as I know, that's the first time where this model was written down explicitly. Okay. And behind all of this, there is some quantum group structure, which I'm not going to say too much about, but basically you don't just get these weights from thin air, you get them from some sort of representation theory of the underlying quantized affine algebra. Okay. All right, so now that we've written down the most general weights, let's say something about the degenerations of these weights. Okay, so a couple of degenerations that are of interest. So the first one is you can set one of these parameters, say the Z, equal to 0. And if you do that, then weights will drastically simplify. Okay, so this is going to be question 3 on the problem sheets, which when the problem sheet is posted, then you'll be able to do this exercise. So it's just an explicit computation, and you find that in that case you get this. Okay, and further from there we can then take t to 0. So if you take t to 0, you see that this thing here, this will basically collapse to an indicator function. All right, so in that case, you find you get exactly the same model that was used for the Q-Whittaker polynomials. So already this model that we've written down will reduce to Q-Whittaker polynomials. And furthermore, in this expression here, if you take n equal to 1, you just get down to the 5-vertex model. All right, so already there are some very nice degenerations of the model as written. There is a sort of dual limit that you can take, which is to take the other parameter x to 0. And this also leads to huge simplifications. In the form that I gave the weights, this limit looks a little bit singular, but it's actually okay, so you can perform this limit. And then find that you get a nice formula for the weights as well. And if you take, again, n equal to 1, then you will get yet another 5-vertex model. So it's a 5-vertex model that's a bit different to the one that we wrote down yesterday. So that 5-vertex model can actually be used to construct the short polynomials via vertical strip interlacing. So previously we had a formulation in terms of horizontal strip interlacing, but there is also a vertical strip interlacing version. Okay, and so in terms of the language of vertex operators that people tend to prefer, this would actually correspond with getting the vertex operators gamma prime plus and gamma prime minus. So these are sort of the notations that people use typically when they're looking at the vertical strip interlacing version of short polynomials. And the full ensemble of gamma plus minus and their prime versions, you can use these to define the most general types of short processes. So I just want to say that, yeah, these other versions of the short processes are also contained in these weights. But in this lecture, we will be looking primarily at one other type of reduction, which is where you set z equal to minus tx. And although it's written in a slightly disguised form here, this is actually the limit to, this is the limit where the horizontal line, so horizontal, basically the line that goes through a tile. So this line here. This corresponds to the limit where this line becomes fundamental. Okay, so in the language of representation theory, that corresponds to basically the simplest type of representation for that particular line of your vertex. So it's like the fundamental or the defining representation. Okay. So are there any questions at this point? All right. Okay. So we'll
actually, I have a question. Sorry.
Yep, go ahead.
So with this simplification, let C equal to T over X or something. So you reduce to the fundamental representation, but the other in general. So what representation are these vertex weight for?
Yeah. So this Z is morally minus T to the J over X. Sorry, I've got this wrong way around. Times X. Okay, so this is this, when you perform this specialization here, you get to symmetric representation of weight J. So that corresponds to where you do fusion with J boxes. Okay, and all I'm doing here is taking J equal to 1. Does that answer your question? So it's written in a slightly non-standard form. So normally you would not have the minus sign and the X here, but I just incorporate them into the Z because it makes things a little more symmetric, as we'll see later. So, but yeah, this is just. Yeah. All right. Okay, so the third example in the catalog of examples will be the non-symmetric whole Littlewood polynomials. Okay, so these are going to be polynomials that will now depend on t, but they will not have a q. All right, so it's just the t here. And the presentation of this is sort of going to get more complicated as we go on. So I want to begin with a very simple motivational example and then go into more depth. All right, so let's consider something completely trivial. So let's take a collection of n balls and arrange them in a straight line. And the balls are going to be indistinguishable apart from a label which we prescribe to them. So every single ball is going to have an integer label. Okay. So more precisely, the ith ball from the left is going to have label mu I. And so the whole line can just be described by a composition. All right, so if you like, you can also think of this line of balls as just being an integer composition. So let's do a little example. So maybe this ball is going to have label 1, this will have label 2, label 0, this can be a 2, this can be another 2, and this could be a 3. Okay, and what we're interested in doing is shuffling the balls around. But when we do this shuffling, these ones here are indistinguishable. So if we perform a permutation here, then it should have no effect. Okay, so now let's look at representations of the symmetric group on such collections of objects. So let's take the symmetric group that's generated by S1 up to Sn-1. So these are just the simple transpositions, and they satisfy these braid relations here. Okay, so we can represent permutations of the balls in terms of space of polynomials in n variables. And the identification is something completely trivial. So all you do is you replace your configuration of balls by a monomial. So for the example that we've done up here, we would have 6 variables, and I would put here x1 to the 1, x2 to the 2, x3 to the 0, x4 to the 2, x5 to the 2, and then x6 will be cubed. Okay, so that's the monomial that I would associate with that configuration. And then the action of symmetric group is just affected by letting the SI permute the 2 variables xi and xi plus 1. So clearly, if I act with SI on x to the mu, then I will get here x with SI mu. And this is just doing the obvious thing, it's just permuting the ith and the I plus 1th part of that composition. Okay. So a very simple example, but this is really the motivation behind the non-symmetric whole Littlewood polynomials. So let's now go to those. So non-symmetric whole Littlewood polynomials are introduced in exactly the same way, except you replace symmetric group by the Hecke algebra of type an-1. Okay, and for people who know this theory well, they will know this corresponds with taking a quantum or a t deformation of the symmetric group. So the Hecke algebra is given in terms of, again, generators t1 up to tn-1, which satisfy this, again, braid type relation here. But then one of the relations gets deformed. So normally you have this relation here where si squared is the identity. Now, if I like, I could rewrite this as si minus 1, si plus 1 is equal to 0. It's another way of writing that relation. Okay, so I can take that relation now and I just t deform it. So that means I'll just replace my minus 1 here by a t. Now if I do that, then I get the Hecke algebra. So that's precisely this relation here. Okay. So this little change ends up having some pretty non-trivial consequences. So one of the consequences is that now if you want to actually find a representation of that algebra, Well, the representation is not going to be as simple now. We'll have to introduce these so-called divided difference operators here. So a valid representation of that algebra is to identify t sub I with the expression that's given here. And the sort of non-trivial part of this is I have to take 1 minus si acting on some polynomial that will give you something which is divisible by xi minus xi plus 1, and then you divide that out. So this will cancel off, and you will preserve polynomiality when you do this. So this is called a polynomial representation. Okay, so now let's play exactly the same game as before. So we'll start off with our collection of balls, which we represent by some x monomial. And instead of acting on this with generators of symmetric group, we'll act on this with the generators of the Hecke algebra. And if you do that, then you get the non-symmetric whole-linear polynomials. So they're a kind of quantum deformation of the example we just looked at before. So they're defined recursively. So you have that E delta is equal to the monomial X delta. So that's exactly the same as the example we just saw. So that's when delta is weakly increasing. Yeah. And in other cases, you have this recursion relation here. So T sub I acting on E mu gives you E with the two parts of the composition exchanged. And that holds whenever mu I is less than mu I plus 1. So you can see that just with these two relations, you can build up any polynomial in the family just by the recursive action of these T sub i's. Okay, and furthermore, the way that you actually recursively build up your composition doesn't matter. So the way that you do the decomposition of your permutation will not affect the result. And the reason why it doesn't affect the result is precisely because you have this relation here. Okay. So those are the non-symmetric whole-linear polynomials. Okay. So what we want to do is come up with a partition function representation of those objects. And in order to do this, we're going to need to be a little more explicit now. So we're going to need some explicit vertex weights, which are given below, and we'll also need a Yang-Backstreet equation. So I'll do both of these things now for this example. Okay. So the explicit vertex weights that we will need, they're given by the vertex weights that we saw previously. So you recall that we had this rather complicated looking expression for those weights that depend on X and Z with A, B, C, and D. And what we're going to do now is replace this Z with minus Tx. Now, if we do this, then we get some simplifications. So the first simplification is that the weight vanishes unless the size of these vectors here. So I take the sum of the components of the vector, and that has to either be 0 or 1. So if it's anything bigger than that, then the weight vanishes. So this is precisely the restriction to fundamental vertex models, because we know that in a fundamental vertex model, the state that lives here and here, there's A and B, they both have to be, well, you can only have one color at the edge is what I want to say. You cannot have multiple colors. Okay, so that's precisely because of the fact that the dimension of this space here, this will just end up being n-dimensional, or n plus 1 dimensional when you're dealing with fundamental representation. And for all of the cases that do not vanish, you can actually work out the weights explicitly, and you get this table here. Okay. So yeah, I'm not going to say too much about the explicit form of the weights because there's nothing too deep to say here. But yeah, basically all of the examples that I've written here, you'll notice that they preserve conservation. So this E sub I, this is just the ith Euclidean unit vector. So it's a 1 at position I, and 0 is everywhere else. Okay, so the only states that you can have along these vertical edges are the Euclidean unit vectors and the vector 0. And if you work out all the cases, then you get the cases given here. Notice that this one, even though it respects the conservation, it actually has a vanishing weight. So this one actually vanishes via some independent means. But all of the other ones are non-zero. So that's the model. And again, we have a very good representation theoretic understanding of where this model comes from. Okay, so let's move on to the Yang-Baxter equation. So Yang-Baxter equation is a very deep equation that basically holds for all of the models that are given in the course, but on this particular model, we'll look at it a little more explicitly. So what is the statement? So the statement is that I have to take some vectors now. So I'll take a vector A here and a vector B here. And I have to put the same vector in the same position on the right-hand side. That's the first thing. And then I will perform a sum over some other vector C. So I also need to, maybe I'll do it this way. So this is sum over C happening on this side as well. Okay? And so C lives here. That's this sort of internal edge. Yeah. And then finally, I need to put some states on this cross. So for the cross, I will just identify, so along the edges of the cross, you can have Euclidean unit vectors. So I'll just identify E sub A with A, where A takes values in, let's say 0 up to n. Okay, this is just to lighten the notation a little bit. So I'll put here AB and CD. And then I have to make the same choice on this side. So I have to put here A, B, and CD. And once again, these internal edges here, which I don't know what we should call them, maybe let's call them F and G. So F and G, you need to sum over these, and likewise, you'll have a sum over F and G here. And probably should do this. Okay. So this is the Yang-Baxter equation. So it has to hold, in particular, for all choices of integers that you put here, and all of these external edges, all possible choices that you can fix. This equation has to hold. So it's actually not one equation, but lots and lots of equations here. And the weight of a cross is something that you need, and the weight of the cross is given by this little table below. Okay, and there's one extra piece of information that you need here, and those are the parameters. So this little tile depends on X, and this one depends on Y. And here this depends on X, and this depends on Y. And in the vertex, Z is identified with Y divided by X. So that's the Z that shows up here. Okay. So the claim is this equation holds. All right, so are there any questions at this point? Okay.
So just to make sure, this is for which Kac-Moody, for which algebra
so this
are we talking about?
This is for you. I should say this is for you. Maybe t to the 1/2 SL1n 1 bar n. Does that answer your question?
Yes, thank you.
But it's not. Yeah. So this algebra has a universal R matrix. And in the universal R matrix, what we're doing here is we're taking different representations of the two lines. So in order to get this tile, we take a fundamental representation of the horizontal. And for this one, we take a symmetric tensor representation of weight I, and then we send I to infinity in some way. So it's some infinite limit here, where this thing basically gets replaced with a Verma module. So yeah, hopefully that answers your question. Okay, so now let's give the main statement. All right, so we're going to define a class of partition functions, so as I introduced partition functions yesterday, or the day before, they were living on a cylinder, or in more generality, living on a torus. So now we're just going to be looking at a purely planar object. So there is no identification of edges that's happening here. That will come back later. So the partition function I want to set up is the following. So I'll have a color sigma 1, sigma 2, up to sigma n, and they're entering along these edges here. So let's just schematically represent this by, so using the language that I gave yesterday, I should represent that with a little dot to indicate insertion into the lattice. So maybe I have something like this. Okay, so each one of those dots has a color label associated to it, and the associations are just these ones. And then what happens is they travel through the lattice and they'll go out somewhere at the top. So maybe let's put them in some positions. And they can share horizontal edges, that's fine. But maybe I get something like this. And so the rule is that color I exits in column mu sub I. Okay, so that's how this thing actually depends on, not only does it depend on a permutation, which is encoded here, but it also depends on a composition, which is encoded along here. Okay, and so these are basically like the two seams that we had in our torus, except now we break it open along the two seams, and we put two states along there. So this is a fairly generic object. And I also need to put some variables on the edges. So let's make this one x1, x2, up to xn. Okay, so that's a partition function that you can now compute using the explicit weights that were given here. And if you do the computation, put it on the computer or however you want to compute this thing, the claim is that partition function, in the case where the permutation is the identity, so namely this is 1, 2, up to n, in that particular case, this thing gives you the non-symmetric whole Edgeworth polynomial. Okay. So we're going to sketch a proof of this. I'm not sure if I'll be able to go through all of the details, but let's see how far we can go with this. All right, so in order to do the proof, we have to show that partition function satisfies the two defining properties of the object. So the family, just to remind you, the family is uniquely determined by these two properties here. So there is an initial condition. So we want to show that we just get monomial x delta in the case where the composition is antidominant. So that's the first thing to check. And then the second thing to check is this recursion relation here. If we can check that the partition function has those two properties, then it has to give you non-symmetric whole Edgeworths. Yeah. So let's do the first one. So I need to put some labels on this thing. So again, this is x1, up to xn, those are the variables. And I have to now put the identity, because the statement holds where this permutation is the identity. So I'll have to put color 1 here, color 2, up to, yeah, maybe let's actually color them in. So this will be a 1. This will be a 2. Will be a 3, and the last one will be a 4. Okay, and we're dealing with an anti-dominant composition. So just to remind you, the path of color I is leaving at the top of column mu sub I. So if you're dealing with anti-dominant composition, that means that the way that the things go out at the top is actually ordered as well. So that means that the first red dot will go out, say, at this position. Then you'll have the blue going out next. Maybe it will go out here. Then the orange, and finally the green. So they have to preserve the ordering, precisely because we're dealing with anti-dominant. And then you actually find that this partition function actually freezes for this particular choice of boundary conditions. And the reason for that is pretty simple. So you look at the motion of the green path, and the green path, it can do just one thing. So again, we're not on a cylinder or on a torus anymore, so you cannot have any windings. So this green path, it has to just do this. There's nothing else that it can do. And likewise for the orange. So it's important to note here that the intersections of these vertical edges, you can only have one path intersecting a vertical edge, because we're looking at the fundamental model. So that means these edges are all saturated. So combinatorially speaking, the orange path has no choice. It just has to do this. And you can iterate the argument now. So you find that all of them, there's just one thing that they can do. And actually, you can just use the weights now and explicitly compute this thing. And what you end up getting is just the product from I equals 1 up to n of xi to the delta I. Okay, so you can really just see this, this initial condition using this factorization property. Okay. So that's the initial condition. Now we have to do the more difficult task, which is to prove the recursion relation. So the recursion relation, I'm going to do it in 2 steps. So I'm breaking things down even further. So we're going to have 2 lemmas now. So the first lemma tells you about the action of the Hecker generators. All right, so what do we have to do? We have to act on our partition function, which is this thing here, and we have to act with T sub I. And the claim is that it gives you this. So what's happening here? So it gives me the same object back again with here a t minus 1. And it gives me this partition function where I end up doing permutation of the colors I and I plus 1. So in one line notation, this Si is just 1 up to I minus 1. I plus 1, and then I. Okay, so that's what's being fed into. Okay, so let's try to prove this. Okay, so I'm not sure if I'll be able to do it in like all of the details, but at least to give you an idea of how it works. So what we'll do is we'll start off by, we'll just draw the 2 rows of the partition function that carry the variables xi and xi plus 1. Okay, that's these 2. And the colors that live on these edges here, this is I and this is I plus 1. And these 2 are, these are zeros. Okay, so what we'll do is we'll take that thing and we'll do a standard trick here, which is to insert a cross. So I'm going to say that's equal to to this thing. Just copy it, put it here. And well, I should probably put it down actually. I need to put it across. So I'll put it across like this. So this is our intertwiner. And the claim is I can put that thing in just by deleting these zeros here and putting instead some zeros like this. Right? Because actually that vertex is frozen. It cannot do anything. So the states that live here and here are completely determined. They both have to be zeros. And the weight of the vertex that has 4 zeros around it is equal to 1. So I can insert this thing. That's the point. Then I use the Yang-Backstreet equation. So Yang-Backstreet equation, let's just have a look at it one more time. So that allows you to take cross that lives on this side and push it through to the other side. And in the course of doing so, you end up exchanging these two tiles, or at least exchanging the variables. So let's do that now. So if I use that relation over and over again, what will happen is the cross will move all the way to the other side. So basically, this will make its way over to here. And it will go here now. It's basically what happens when you use Yang-Backstreet equation after lots and lots of steps. And the end of the argument is now to basically look at what can happen at this vertex here. And for this vertex, you find that there are two possibilities here. So the two possibilities, I'll put them here. So this is the first one, and this will be the second one. So I have that this is equal to this plus this. And so in the first case, I have the color I plus 1 coming here, and then color I coming here, and then this is the opposite. Okay, so each of those vertices, so this one here and this vertex here, you can work out the weights explicitly. So the weights are given by that table that I gave before. So this table. Okay. So if we use the weights in the table, and you can work out this quantity explicitly. And what it gives you now is a relation between the original partition function and the partition function where you have actually exchanged I and I plus 1. And if you note, that's exactly what we wanted to do, actually. We wanted to exchange I and I plus 1 because in the statement, we had this permutation here. So basically the identity gets changed into SI. And so there's a little more work that needs to be done. Once you actually tidy things up now, you'll end up precisely proving this relation here. You can see already that it's sort of starting to resemble that expression. Okay. So this is sort of the sketch of how this works. All right. So that's all well and good, but it doesn't really complete the proof yet because all we've done here is act with Ti on the partition function. But what we need is when we act with Ti, so if you recall, what we're trying to prove here is that Ti acting on Z identity mu, we want this to give us Z identity Si mu. So we want the permutation to actually happen here. And at the moment, we don't have that. We have the permutation happening up here. And besides, we have already here a sum of two terms. So we haven't really proved this yet. Okay, so that's why we need the second lemma. So the second lemma says that provided that you have a composition mu such that mu I is less than mu I plus 1, then that right-hand side that we just saw, that right-hand side can actually be re-expressed as precisely the quantity that we want. Okay, and this lemma, this follows from something called color blindness. Okay, so I will sketch the proof of how this lemma works, and it has a very sort of simple geometric encoding. So you can understand graphically how what this thing is actually saying. The proof itself is, you have to be a little more explicit, but graphically it's easy to understand this statement. Okay, so I'll take that relation and I'll just rewrite it a little bit. So I want to rewrite it in this form here. Okay, so it's some relation involving those partition functions, saying that this difference of partition functions is equal to this difference here. Okay, so let's look at this difference first. So in that difference, what is happening? So the composition that lives in both of these partition functions, this composition is fixed. So this is not changing, but what is changing is the permutation index. So let's represent this graphically. So I'll have a little path that exits here and which exits here. And somewhere else I'll have another path here and here. And so these two paths, they correspond with, so this is corresponding with a part mu sub I, and this one is corresponding with mu sub I plus 1. Okay, so those are the two parts of the composition that we're interested in exchanging. And note that they're in the same positions in both of those diagrams. And then entering along the left boundary, I will take here path here. So this is the path of color I plus 1. Actually, maybe I should put this down here. So here is I plus 1, and here is I plus 1. And here is I, and this is I. And I'm taking the difference of those two things. So it's this minus this. Okay, so that difference there represents this left-hand side. Okay, because I'm fixing the composition, that's fixed. But what I'm doing here is I'm shuffling these two colors around. So that's the one thing, and we want to prove that that is equal to this. So let's have a look at that thing now. So for that thing, the permutation is fixed to be the identity in both cases. So that means that along the left boundary, we have this. So this is I plus 1, and this is I plus 1. And this is I, and this is I. So those are the same, but what changes now is the two parts at the top. So at the top here, I will have, this is now going to be mu I. And this will be mu I plus 1. Okay. And then down here, I'll have this and I'll have this. Okay, and I'm taking the difference of those two things with a factor of t. All right, so the claim is that somehow this is equal to this. And the reason why those two quantities are equal is there is a sort of thing that lives in the middle, which is called the color invariant version. And so the color invariant version is just where you have all of these being the same color. So all of these being of color I. Okay, so the claim is that that difference of quantities you have here is equal to this version where I just replace everything with the same color. And the claim is that's also equal to this. So there's this sort of object that lives in the middle that allows you to prove the correspondence. And so this is a color blindness, because the object that lives in the middle is somehow, it no longer sees the distinction between the two colors. Okay. So using this lemma here in conjunction with the previous lemma, we end up proving the recursion relation for the non-symmetric whole limits. Okay, so that's the end of that example. So if there are any questions, please ask them now. To conclude the lecture, I wanted to say something about how you can put everything together now and define a generic Q and T theory, which sort of brings together these two notions of temperature that we've been talking about. And so these now will be the symmetric Macdonald polynomials. And this is a construction that has been known now for already 6 odd years, I think. But over the years, there have been some sort of improvements to it, some incremental progress that has changed the original nature of the formula into something a little bit different now. So the version that I'm going to give today is really I guess the state of the art in terms of the formula that you can find for this. Right. So the way that we're going to proceed is via the theory of non-symmetric Macdonald polynomials. So the non-symmetric Macdonald polynomials, they're just Q deformations of the polynomials that we've been talking about, the non-symmetric whole limits. And these are normally defined in terms of the Daha, so the double affine Hecke algebra, which we actually saw in the talk this morning by Wei Ying. So in the Daha, you have some generators, which are called the Cherednik-Dunkel operators. And these are expressed as a product of Hecke generators and their inverses, combined with this generator here, which is the omega. And omega has quite a simple action on polynomials in variables. It acts on a function in variables and cycles the variables around. So think now again in terms of cylinders and circles. It's really the natural geometry for thinking of these objects. And so now, yeah, you have a cyclic permutation of the variables, and the final variable, or the x1, gets scaled by q. So that's the action of omega. All right. So now we have the definition. So let's fix an anti-dominant composition. So again, this is going to be a weakly increasing sequence of non-negative integers. And the non-symmetric Macdonald polynomial E delta is then the unique polynomial such that when I act with yi on E delta, I get E delta back again. So this is, in other words, the joint eigenfunction of the yi operators for I taking values from 1 up to n, with this particular eigenvalue. So the eigenvalue in this case is particularly explicit. So in particular, it's just q to the delta I, the ith part of the composition, and then you have some explicit t power as well. Now you can define non-symmetric Macdonald polynomials for generic compositions. So I've actually only given the definition here in the case of anti-dominant compositions. If you want to do it for generic compositions, again, as we saw in the talk by Wei Ying, you have a similar formula. It's just that the eigenvalue becomes a little more complicated. So I just wanted to give this one because it's somehow the cleanest for the presentation. And besides, it's the only one that we'll actually need. Okay. So now here is the theorem. So we're going to revisit the partition function that we just looked at before. So just to remind you. So in the case of an anti-dominant composition, you have this formula here, completely factorized expression. And what we're going to do now is take that expression and restore the cylindrical geometry. So we're going to think of this thing as being living back on the cylinder again. So we're going to permit paths to wind around columns once again. Okay, so in other words, we're going to restore those fugacities that correspond with the crossing of this seam. So those fugacities are now going to be non-zero. And so the claim is, if you do this, then you get precisely the non-symmetrical Mcdonald polynomial. So I'm just going to save myself some work. I'm just going to copy this. And yeah, I'll just put it here. So this can go away. And so this is the claim. So I should now remove these paths at least, because the configuration, this is not frozen anymore. Precisely because of the fact that you can wind around the cylinder, this thing does not have just a frozen partition function, but some non-trivial object that you have to compute. And in terms of the notations that I gave, so these winding fugacities, these betas, we identify them with q to the delta c minus j. So this is, to remind you, this is color C, which winds in column J. Okay. So once again, this kind of geometric progressions in Q. And so the claim is that that gives you E delta. Well, it gives you E delta up to some normalization. So there is a normalization floating around here that needs to be computed explicitly, but given that in the definition here, it was only up to normalization anyway, this normalization constant is not particularly scary. Okay, so I want to sketch the proof of how this works. So yeah, before I do that, let me make a few remarks about this. So the original version of this formula, so this goes back to 2015 in a paper that we had with Luigi Cantini and Jan de Geer. And we gave an explicit formula there, matrix product formula, for this E delta, precisely in the case where you look at an anti-dominant composition. But that early work had some differences compared with what I've presented here. So the two differences, well, really the main difference is it used a model there that was bosonic, instead of the fermionic model that we're using here. So in particular, the bosonic models, they're models where you can have basically arbitrarily many windings. So the particles can wrap basically infinitely many times. So that was the first key difference. And this result only held for mu is equal to delta. So for anti-dominant compositions. Then in 2019 with Alexei Borodin, we actually generalized this result, this matrix product formula, and we managed to find matrix product representation for non-symmetric Mcdonalds for arbitrary compositions. So not just for anti-dominant ones. And then in the even more recent work here, we basically converted all of this formalism into the fermionic language. So the claim is that if you do the same types of computation using the fermionic vertex models, you also get non-symmetric Mcdonalds. And the fermionic version is nicer in the sense that the windings around the cylinder now, this is just finite windings. Every single particle can either wind or not. So it's really a very finite object and very easy to compute. So this is really I guess the history of this result. Okay. So let's try and sketch how the proof works now. So I think I started at around 5:05, so I'll probably go for another 15 minutes. Okay. So yeah, the first thing that we're going to need to be able to do is compute the action of a Hecke generator and its inverse on these types of partition functions. So you need to be able to compute it where the permutation that lives here is now generic. So this permutation here is the identity, but of course I can generalize to the case where these things are a generic permutation now. And actually, if you do that, you get something which, again, Wei mentioned in his talk. So changing this to sigma, this gives you the what's called permuted basement non-symmetric Macdonald. Okay, so we need to understand how to permute the basement. That's the first thing we have to be able to do. And the second thing we have to be able to do is to compute the action of omega on these partition functions. And this is slightly more involved. But of course, those are the two things that we need, because if you look at the Cherednik-Dunkel operators, that's what they're composed of. So they have the Hecker generators and their inverses, and you also have this omega here. So basically, we're trying to prove this eigenrelation. Okay. So for the action of Tj and Tj inverse, this is actually pretty simple to do. So we have these two statements here, which I've grouped into the one lemma, which says if I act with this train of inverse Hecker generators on the partition function, then what does it do? Up to a power of t, it will send color I, which used to live here, it will send it all the way to the end. So if you think in terms of the pictures, so you have your partition function, and color I starts off entering here, makes its way up to here, and leaves in column delta I. But if I act with these Hecker generators now, what will happen is you push this thing to the top. So the I will now make its way up to here, and all of the other ones will be ordered. So this will be 1, 1 up to I minus 1, then I plus 1 up to n. And actually, this action here, we've already proved this action here. So this is essentially a consequence of something that we already saw. So this might be a little bit confusing now, but in this relation that we already proved, I can rewrite that relation. So I can just take this t minus 1 and bring it to the other side, and then I get ti minus t minus 1 acting on z identity mu is equal to z si mu. And for people who know the theory well, you'll recognize that that quantity there is nothing but the inverse of, so this is nothing but ti inverse multiplied by t. So actually, we have already proved that the inverse Hecker generators, they have a nice transforming action on these partition functions, and they end up just permuting the colors along the left. So these two statements, namely this one here where I do this permutation, and the second one where I do an analogous permutation, the color I all the way to the bottom, these two statements are easy to prove. Okay, so that's basically how that lemma works. We've really already proved it. Okay, so now if you look at this, we have actually an understanding of two of the pieces in the Cherednik-Dunkel operator. So we understand how to act with this train of Hecker generators, and we understand how to act with that train of Hecker generators. And both of those are present in the Cherednik-Dunkel operator. So if we go back to it, here's the first one, and here, if you like, is the inverse of the second one. So really, we have all of the pieces now. We're just missing the omega. And what the omega is going to allow you to do is to prove an equality, so a kind of equality between these two things. It will precisely allow you to take this row now and bring it all the way down to the bottom. And you should think in terms of the cylinder now. So really what's happening is the omega it has an action now on this thing where it turns the cylinder in a sense. So omega really takes this thing and rotates it around. So it's sort of spinning around now, and then you end up with the I being at the bottom. So that's how the action of omega is going to work. Okay, so here is the second lemma. So we have this quantity here. So that quantity, this thing is exactly omega acting on the z that we just computed. So with 1 up to I minus 1, I plus 1 up to n, and then I. Okay, so this is precisely the action of omega. And what we're going to do is prove that that's equal to this one. And that thing is exactly the quantity that showed up in the second part of the lemma. So we're going to prove the equality of these two things up to this power of q. And remarkably, the way that you can prove this is purely bijectively. So there's actually a bijection between every single lattice configuration here and the lattice configurations here. So there's really a one-to-one correspondence, and that one-to-one correspondence preserves the weights. So the weights of the configuration end up being exactly the same. The only difference is they differ precisely up to this q to the delta I. So it's this remarkable weight-preserving bijection between the configurations. So I'll show you what the bijection is. So let's just do an explicit example. So let's assume that I in this case is equal to 3. So I'll have a 3 at the top. And the other ones should be ordered. So this will be a 4. This will be a 2. And this will be a 1. Okay. And the x variables, so this is x2, this is x3, x4. No, sorry, I think, yeah, that's correct. And this one should be qx1. Okay. And on the other side, I'm going to have x1, x2, x3, x4. And color 3 will come to the bottom now. And will be a 2. This will be a 4. And this will be a 1. Okay, so already you can see it's a kind of, there should be some sort of rotation which is happening here. And all that's happened is this qx1 gets replaced with x1. Okay, so let's do an explicit example of how these paths might wind. So maybe this 3 would do something like this and terminate in this column here. And the 4, maybe the 4 does something boring. Now let's say the 2 does something more interesting, like wrapping around. And maybe doing something like this. So it terminates here, and this one terminates here. And let's say the 1 does something boring. So that's the kind of configuration that you might see typically. And what the rotation is just to take that thing and just rotate them now. So really think of it as living on a cylinder, and just in your head rotate the cylinder and see what happens to the paths when you do this. With the caveat that the crosses stay at the top. So it's a rotation, but somehow the seam always has to be at the top. So if I do this rotation now, you'll get the following picture. So the blue line will just go to here. The green line will wrap around and do this. Like this. The red line will do something boring And the orange line will now, so previously it wrapped around the cylinder here, but when you actually turn it around, that wrapping sort of goes away. And now it will just end up doing something like this, if I've done the wrapping correctly. So what you do is you work out the weight of those two configurations now, and the claim is that those two weights are equal. They're exactly equal up to this q to the delta. And in this case, delta is equal to 0, 1, 2, 3. So q to the q cubed in this case. And so that's how it works. You just use this bijection on every single configuration, and you prove this thing really term by term. Okay. So that lemma combined with the previous lemma, that completes the proof. So that proves the eigenrelation for the non-symmetric Mcdonalds, and therefore the object that you have up to normalization has to be the non-symmetric Mcdonald. Okay. Are there any questions on that procedure? Okay. So now let's head towards the end. So as a corollary of this, even though it's not completely trivial, you actually end up getting a formula now for the symmetric Macdonald polynomials. And one of the nice things about this fermionic presentation that we've given here is that the object that you get here is actually the symmetric Macdonald polynomial in the integral form. So integral form, this is sort of celebrated form for the Macdonald polynomials in algebraic combinatorics. That is precisely the form where you get, for example, Macdonald positivity conjecture, which has now been proved. So somehow the fermionic formula is really the natural one for getting the integral form of the symmetric Macdonalds. And so the claim is now, I set things up as follows. So I have x1 up to xn. And again, I'm going to have my partition that lives along the top. So again, you'll have that color I exits in column lambda tilde I. So this is using this lambda tilde, which I defined in the previous lecture. So please revisit that if you need to see what this means. And the boundary conditions, all of the colors here, 1 up to n, they all enter in this column. So I have, this sort of thing. And then they propagate through the lattice with the windings, and then they make their way at the top in a way that encodes the partition. And the claim is if you do this with the same winding fugacities as before, you get precisely the integral form of the symmetric Macdonalds. And again, this is just a variant of a formula that we already had in 2015 with Luigi and Jan. So really, this is kind of rehashing of that, but presented in terms of the fermionic vertex models. And as a corollary, if you send t to 0, you just end up getting the Q-Whittaker polynomials. So that's precisely the formula for the Q-Whittakers that I gave in the first lecture. Right. So yeah, I think this is a good point to wrap it up. So I wanted to say something about, so there are some supersymmetric analogues of the Mcdonald polynomials that depend on 2 alphabets now, the x's and the z's. And I wanted to make the point that those vertex weights that I defined back at the start of the lecture, if you keep both the x's and the z's, then you end up getting the supersymmetric Mcdonalds. And those are nice because they actually degenerate to the ordinary Mcdonalds in 2 different ways. So if you want to know more about this, so we did this in a paper with Sasha Gabali, And I think this is dating from 2018 or 19, I can't remember precisely, but that's where we're looking at these supersymmetric analogues. And from this, you can also go to the theory of other symmetric polynomials, such as LLT polynomials. I promised to say something about LLT polynomials at the beginning of the course, but I think that kind of running out of time, so just save that for another course. So yeah. All right, so let me wrap up with some future prospects. So these are just basically some things that sprung to mind while I was preparing the lectures. This list is by no means exhaustive. There may be other interesting problems. So, and somehow this is in order of apparent difficulty. So really the first thing on this list I would say is that these supersymmetric Mcdonalds that depend on the two alphabets, they're interesting because they degenerate the order ones by two reductions. And this is the one that we've looked at in the lectures here. So where z is equal to minus tx. But there is a second reduction, and that reduction is not so well studied. And in particular, it would be interesting to look at that reduction with respect to the underlying non-symmetric Macdonald theory. So I think that there's some interesting territory there. Another possibility is to look at other types of reductions. So we've really looked at reductions to Hall-Littlewood and Q-Whittaker, but another reduction that has also been topical in these lectures, well, in the lectures by Vadim, is the reduction to Jack polynomials, which you get by setting Q equal to T to the gamma and then setting T to 1. And as we've seen in Vadim's lectures, there are even further degenerations of those to these multivariate Bessel functions. So I think that it would be nice to come up with some sort of stat-mech interpretation of, for example, the multivariate Bessel functions. One could also think of performing these kind of computations in the case of the Q-Whittaker polynomials. So Q-Whittaker polynomials degenerate to the classical GLN type Whittaker polynomials or Whittaker functions in the case where you have to perform some scaling of the partition. So I think that these sort of scalings and degenerations, there's something that it must be interesting to see how this works actually on the lattice model. So these are things that should be understood. Slightly wild question here, but it sort of stems back to the to the original presentation that I gave in these lectures here, where we're looking at these toroidal boundary conditions. Can one actually define and study some sort of toroidal version of Macdonald polynomials where you have this double periodicity? So I think this is an interesting direction, and there are other directions. So try to find partition function representations of, for example, interpolation Macdonald polynomials. These are objects that have vanishing properties that uniquely characterize them. And so it would be really nice to have a partition function representation where you could actually see the vanishing properties directly from the lattice. So this would be really cool. And some other problems that some of us in the audience have thought about for some time, not too much progress here, is to try and do this for other root systems. So I have nothing to say about that for the moment. And then really, I think the hardest item on this list here, it concerns the expansions of LLT polynomials into the Schur basis. And these are known to have positive coefficients, and there is no combinatorial formula for these coefficients. It sort of feels like this problem should be accessible via the framework that we've sort of set up here. But to date, yeah, there's no progress on this either. So yeah, that's really the summary of the future prospects, and so we can have some questions now. So thank you very much for coming along, and yeah.
Let us thank Michael for his course and for this second talk in particular. Are there any questions? So I have a small question. This degeneration to jack-like objects. You have a paper on this recently, or is this not what that? There is a paper of you and Bogodin on polymer limits, but is this not what you're studying there?
Oh yeah, sure. I mean, yeah, it's true, but it's not exactly the limit that I have in mind here. So yeah, I mean, I really.
Yeah, so polymers are not jack, but they're sort of the similar limit.
Polymer is more related to like limits of Q Whittakers, right? So
yeah,
like that's like Whittaker limit. So yeah, I feel that yeah, both the Whittaker limit and the limit to multivariate Bessel, they sort of live in the same universality class somehow. So both of those should be accessible. But it's going to involve some sort of rescaling where you don't just have like discrete, discrete type lattice objects. You'll actually have, the partitions now will be like tuples of real numbers. So it's going to be some sort of continuous scaling. So I'm not really sure how it would work out, but I think that this should be doable. So